Just take a look around you for a second. Seriously. The desk you're at, the screen you're watching this on, the air you're breathing right now. Have you ever just stopped and wondered what all of it is really made of? What is the basic stuff that makes up our entire universe? Well, scientists have a name for all that stuff. They call it matter.
And this really says it all, doesn't it? The ground beneath your feet, the air around you, and the stars in the sky are made of matter. You are made of matter too. It's literally everything. It is everything.
And the sheer variety of matter is just mind-boggling. I mean, it can be unbelievably powerful and explosive, like in a rocket launch. That's just matter being converted into pure, immense energy through chemical reaction. But then, it can also be incredibly complex and alive. This links, right, all of its biological wonder, from its twitching muscles down to its very DNA, it's all just another beautiful, intricate arrangement of that very same fundamental stuff. And of course, matter can take on all sorts of different forms or states. Look at this iceberg. You've got solid and liquid right there together. Now here's the amazing part. As different as a rocket, a cat, and an iceberg all seem, they can all be broken down and understood. And that's exactly what we're going to do today.
So let's dive in. Section 1, what is the world made of? Now, to get a handle on all this variety, scientists like to start by sorting all the stuff in the universe into a couple of big, basic categories.
And the first big split is this one: pure substances versus impure substances, or mixtures. A pure substance is made of only one kind of thing. Think of a bar of pure gold. A mixture, on the other hand, is just a bunch of different things all jumbled together, but not actually connected chemically, like, say, a bowl of trail mix.
And this is a perfect example. On one side, you've got a diamond. That is a pure substance. It's just carbon atoms and nothing but carbon atoms, all locked together in this perfect, strong structure. But on the other side, ice cream, that's a classic mixture. You've got milk, sugar, cream, water, maybe some chocolate chips. They're all just physically hanging out together, but they haven't chemically bonded to make some new ice cream substance. It's delicious for sure, but from a chemistry point of view, it's delightfully impure.
Okay, section 2, journey to the atom. Now this is where it gets really fun. What if we could take any of these things, the diamond, the ice cream, anything, and just start zooming in, and keep zooming in, and zooming in even more? What would we eventually find? Let's take that trip.
So let's start with something super simple, like a piece of paper. If we zoom in, we see it's made of tiny cellulose fibers. Okay, let's zoom in on a fiber. We find these long, chain-like cellulose molecules. And what are those molecules made of? Well, we finally hit the atoms. In this case, lots of carbon atoms. But wait, we can go deeper. Inside that atom is a tiny, dense nucleus. And what's inside the nucleus? Protons and neutrons, which themselves are made of what we think are the truly fundamental bits, quarks. Wow. From a piece of paper all the way down to quarks in just 6 steps. That is incredible.
So here we are. We reached the atom, the basic unit of all this stuff. And this is a great little diagram of a carbon atom. Right in the middle, you have the nucleus, packed with positively charged protons and neutral neutrons. And then, buzzing all around that nucleus in this kind of energetic cloud, you have the negatively charged electrons. For a stable carbon atom, the numbers are nice and even: 6 protons, 6 neutrons, and 6 electrons.
Now get ready for this, because this fact never fails to blow my mind. An atom is almost entirely empty space. Here's a great way to think about it. If you blew an atom up to the size of a giant football stadium, the nucleus, which has almost all the mass, would only be the size of a marble sitting on the 50-yard line. The rest is just empty. So you might be asking, if everything is 99.99% empty space, why can't I just walk through a wall? Well, it's because the electron clouds of the atoms in the wall violently repel the electron clouds of the atoms in your hand. That feeling of solid is actually a massive electromagnetic force field pushing back at you.
Which of course leads to a pretty big question, right? If atoms are these tiny, mostly empty little things, how in the world do they stick together to build, well, everything we see? The answer is all about the secret language of the universe: chemical bonds.
The first kind of chemical glue we're going to talk about is the ionic bond. This is what happens when one atom literally gives away one of its outer electrons to another atom. When that happens, you get one positively charged atom and one negatively charged atom. And just like magnets, opposites attract and they stick together. A perfect example of this is plain old table salt. You have a sodium atom that's just desperate to get rid of its one lonely outer electron. And you have a chlorine atom that would love just one more electron to feel complete. So sodium gives its electron to chlorine.
Now sodium's positive, chlorine's negative, and click, they snap together. Do that billions and billions of times and you get a beautiful little salt crystal.
But what if atoms aren't into just giving away their electrons? Well, then they share, and this is called a covalent bond. It's kind of like two atoms shaking hands, but instead of hands, they're sharing a pair of electrons. This sharing holds them together very tightly in distinct little packets we call molecules.
And you know the most famous molecule of all time, right? Water, H2O. It's built exactly this way. You've got one big oxygen atom, and it shares electrons with two smaller hydrogen atoms. And those strong, shared covalent bonds are what hold it all together. This kind of bond is pretty much the foundation for the chemistry of all life.
And then we get to the metals. They do their own thing. They have a really special trick called the metallic bond. What happens here is that in a chunk of metal, all the outer electrons just kind of detach from their individual atoms and form this big, free-flowing sea of electrons that washes over all the now positive metal ions. This sea of electrons is what holds the whole metal structure together so strongly. And because those electrons are free to move anywhere they want, that is exactly why metals are so good at conducting electricity and heat. That sea of electrons is like a superhighway for energy to travel through. Okay, let's zoom all the way back out for our last section. Section 4, the future of matter. Because our understanding of all this stuff is far from complete. It's an amazing, ongoing story of discovery, taking us from thinking the world was just a few simple elements to actually designing the materials of tomorrow. I mean, just look at how fast our knowledge has grown. In 1869, Mendeleev brilliantly organizes the elements he knew about and even predicts ones that hadn't been discovered yet. Flash forward to 1985, and we're finding totally new forms of carbon, like these buckyballs. And then, in 2004, another huge leap. Scientists create graphene, kicking off a whole new age of material science. So what can you do once you really understand atoms and bonds? You can make something like graphene. It is a sheet of carbon that's only one single atom thick. And yet, it is 200 times stronger than steel. Let that sink in. This is the kind of thing that leads to flexible phone screens you can roll up like a newspaper, super efficient batteries, and medical devices that are lighter and stronger than anything we can imagine today. So in just a few minutes, we've gone from the ancient idea of earth, air, fire, and water all the way down to the subatomic world of quarks, and then zoomed all the way back out to designing materials that seem like they're straight out of science fiction. It's just a breathtaking story of human curiosity, and it leaves us with one really exciting question to think about. What will we build with next?